Hello, my name is Chad Houston, and again, we're going to be going over PV NERT and with that, the ideal gas law, but specifically how it deals with stoichiometry and a little bit of Dalton's law of partial pressure. So, when doing this particular assignment that I have set up for you, whenever it says, and this is kind of important, whenever it says gas collected over water, this is a key one. What that means is that we have the gas that we're trying to study. But unfortunately, there's a lot of water vapor mixed in there. And we only want the pressure, volume, and temperature of the gas we want, not of the water vapor, because that'll throw off the number of moles. So what we can do then is if we know the total pressure, we can subtract out the pressure of the water vapor, that is the pressure due to that vapor, to get just our gas. How do I know what that pressure is? You have to have this thing right here, which basically says for any temperature, here's the pressure due to just the water vapor. And because of Dalton's law of partial pressure, we know the total pressure is the pressure of all the gases in there, our gas as well as the water vapor. Really important also, number two, if you don't balance the equation, nothing's going to work. Number three, if you're ever in doubt, always convert to moles. Number four, you can use PV NERT. Another way to solve problems as well is that if we can convert the conditions to the ideal to STP, standard temperature and pressure, we know that 1 mole of any gas at STP is 22.4 liters. Nice thing about that, that's a nice conversion factor. And finally, PV NERT, that's the equation we'll be using. And don't forget, this is key here as well. The units on the gas constant, you have to pay careful attention because we need to have unit agreement. We need to have things in atmospheres. And again, this is in kPa. Don't forget 101.3 kPa is 1 atmosphere. Kelvin, typically they tell you stuff in Celsius. So, okay, so here's some tips and tricks. You've got a mixture of these gases, and they give you the grams of gases that occupies the container. The total pressure is 900 millimeters of mercury. Find the partial pressure exerted by each gas. Okay, so step number one. Avogadro said, same temperature, pressure, volume. We have the same number of moles of gas. First thing I would do, convert all these to moles. And know that if we take a look at this, okay, that we said PV is nRT, okay? Well, in this container, the only thing that they're talking about are two things. And let's isolate those. We're saying pressure over moles is RT over V. This whole thing, the temperature, the volume, and R is constant. So essentially, this comes down to a proportion. And if we're talking about Dalton's law of partial pressures, we know that the total is all of the other gases combined. Well, if it's a proportion, we could say the same thing about the molar fraction as well. So that might help. Number two says, hey, what is the volume of a mixture of 0.4 moles of nitrogen and 0.1 mole of oxygen at STP? What's the volume at 27,760? Okay, so here's the easiest way to solve this. This right here is kind of a trick question. Basically, these right here, it doesn't matter what the gas is. What matters is just the total number of moles. That's all that matters. And they want the total volume for whatever moles is in there. So because these things are so far apart, the sizes really don't matter. So that's why, hey, look, this is, we just need to add, here's the total moles. Here's temperature and pressure. We can find volume. Again, going back, remember at STP, whatever moles that you have is going to be 22.4 liters. Then, once you know the pressure, the temperature, and the volume at STP, well, this is the new pressure and the new temperature. What's the new volume? And don't forget, 760 millimeters of mercury is the same as 1 atmosphere, which this is. So again, 760 millimeters of mercury is the same as 1 atm, which is the same as 101.3 kPa. Okay, moving right along. A gas is collected by displacing it over water. That's a key. Levels of water and inside are equal. You've got a volume of gas. The temperature of the water. Okay, so the temperature of the water, we can assume the temperature of the water and the gas is the same. So we've got that. And we have a pressure. Okay, so I'm going to give you some hints here. What's the pressure caused by the water vapor? Check out your chart that I just gave you at the top of this. If we have a temperature in Kelvin, we can look it up, or in Celsius. I think it's in Celsius. What is it? Yeah, it's in Celsius. We can find it and say, what is that pressure? Now for this one, pressure of the vapor, pressure of the dry gas, it goes back to this. Total pressure, which they gave us, which is, total pressure equals pressure of the dry gas plus the pressure of the H2, the partial pressure of the water. Those are the only two gases in there. You should be able to solve for this. This is the one we would like to use. What's the volume of gas at STP? I have the temperature of standard temperature, standard pressure. I should be able, if I can figure out, so for this one, for what's this, the volume at STP of any gas, if I have if I could solve for the number of moles, I should be able to solve for the volume at STP. And then if I know the moles in the gas sample, don't forget 6.02 times 10 to the 23rd equals 1 mole. So those are some hints on how to solve that particular problem. Let's keep on going. A rigid container of 5 liters. That means the volume's not going to change at STP. Okay, so we have, for this one, we have volume, check, temperature, check, and pressure, check. And it's at STP. Okay. How many moles of nitrogen are present? How many molecules are present? Okay, so here's the plan. If I have standard temperature, if I have standard pressure, I know the volume is 5 liter tank. One of the things that I can do then is I can go ahead and set this up and say, remember that 22.4 liters at STP is 1 mole. Okay. Number 5, how many liters of hydrogen can be collected by the displacement of water? Again, that's a key one. 752 milliliters of mercury, grams of aluminum, excess HCl. So step number 1, you have to balance the equation of aluminum plus HCl. Okay, so you should be able to do that. Make sure you get aluminum likes to go to +3. Number 2, if I have grams of aluminum, I can get to moles of aluminum. Okay, and again, this is going to go to H2 and you'll have to balance it. If I have moles of aluminum, I can use the mole to mole ratio, which is, this is unbalanced right now, to get the moles of H2. Okay, now let's think about this for a second. I have a temperature. I have a total pressure, and I can take out the water, right? The vapor pressure due to water. I can subtract that out, and I have moles. So I've got moles of gas of H2. I've got the pressure of my dry gas because I've subtracted out. I've taken out the water. Pressure. What else? We need temperature. I've got temperature in Kelvin. Okay, that's everything I need to solve for volume. Okay, let's keep going. How many grams of potassium chloride are required to produce 30 liters of O2, 27 degrees Celsius, and 745 milliliters of mercury? Okay, so again, you have to balance the reaction. I'm not going to, so we balance the reaction. We're going to get the potassium chloride. We'll get that here. That's going to go to O2 and plus KCl. Okay, so you balance the reaction, and we're trying to find grams. Okay, so here's the deal. Currently, for this one, okay, and it doesn't say it's over water. We have volume, we have temperature, and we have pressure. You can solve for N. If you solve for N here, we know N of the potassium chlorate. Once we know that, we can go to grams. Okay. Next one, and we'll do just a couple more of these because I'm starting to run out of time here. But it says how many grams of copper need to produce 224 liters of nitrogen NO gas collected by water displacement over 29,748 according to the following reaction. Okay, so here's the plan. Really quick. Okay, we're looking for grams of copper. This is the big one. Okay, grams of copper. So let's think about what we have. This is the balanced reaction. I've got my volume of NO. There's my NO. I have the temperature of the NO. There's my NO. There's the temperature. I have the total pressure of the wet gas. If I subtract out the water vapor, I've got pressure. Okay. You can solve then. And again, this goes back to PV nerd. Okay. We have everything we need, the temperature, the pressure of the dry gas, and the volume. Unit agreement, solve for N. If I have N here, I look at the ratio, it's a 2 to 3 ratio. Find moles of copper and then grams of copper. Okay, so most of these kind of follow that same process. Okay, follow the same process. And then we get into stoichiometry down here a bit more. Okay, so we'll spend a lot of time working on these problems. I hope this helps. This is just a little tutorial to kind of get you thinking. Again, think PV equals nRT. That's the first one. And then remember the total pressure in all of these. If it says collected over water, is the dry gas plus the water vapor. This is vapor. You want to subtract out. Always take the total minus vapor because we only care about the dry gas. Hope this helps in getting you started. I'll hopefully answer any more questions when we talk in class.